Okay, well, folks, I think we'll get going. Welcome to the first talk of the afternoon session. Today, we're extremely lucky to have Jonathan Liu from Stanford University as the wonderful title, A Tale of Two Tales. Jonathan.
Thank you very much. Let me first thank the organizers for the very kind invitation. It's very nice to be in this wonderful conference. And thank you, Martin, for the introduction. And indeed, today I'm going to tell you a story about two different kinds of tales. So I should also maybe thank Siyuan for giving a nice talk this morning that partly introduced the subject that I'm going to talk about. So these are tales that's related to the kind of tales that you have heard this morning. But I want to tell you a story that there are actually two kinds of tales, and I want to explain what I mean. Okay. So this is a rough plan of the talk. I'll first try to motivate the talk using strong cosmic censorship, and then I'll explain the two tales. So one tale is one that we have sort of seen in this morning, which are the Price's law tale. I would look at it at first in this very special case of Schwarzschild, and then I'll tell you that there's another tale when the spacetimes are dynamical, and then I'll tell you exactly what the theorem is and what it means, and then I'll tell you something about the proof. Okay, so that's the plan. And maybe I should say on the outset that the main result that I'm going to talk about is a joint work with Sung-Jin Oh from Berkeley. Okay, so let's begin. So the motivation of the talk is the following. So just consider the most standard asymptotically flat black holes that we know, Schwarzschild and Kerr. And just by looking at them, you see that they look different. Schwarzschild has a singularity deep inside the black hole, while Kerr, in its maximal Cauchy development, does not have any singularities. Instead, there's a smooth Cauchy horizon. Okay, so if you just look at them, they look different. And there's a conjecture of Penrose, which roughly says from the pictures above that it is the Schwarzschild case that should be generic instead of the Kerr case. Okay, so one sort of modern mathematical formulation of this is to say that if you look at generic data, now you solve the Einstein's equation, you look at the maximal Cauchy development, and well, the maximal Cauchy development should be inextendable as a suitably regular Lorentzian manifold. So Schwarzschild will satisfy this because you cannot extend it. Things blow up here. Kerr doesn't. Okay, so in particular, if this conjecture were to be true, then Schwarzschild is expected to be generic but not Kerr. Okay, and in fact, you expect that if you perturb Kerr data, then you should have singularities in the black hole interior. Okay. So what do we know about this conjecture? Well, one thing we know now already a few years back is this result I had with Michael Staffirmus, which says that, well, despite the expectation that Kerr interior should be unstable, there's a certain feature that is in fact stable. And this is the theorem. The theorem says that suppose you look at the nonlinear solution to Einstein's equation, and suppose you have an exterior region which converges to Kerr. So you're not exactly Kerr, but you converge to Kerr. So this, for instance, arises when you perturb Kerr data. Well, then in fact, the interior would still have a null Cauchy horizon. So the picture will still look the same as previously. And in fact, the metric continuously extends to the Cauchy horizon. And in fact, if you just look at the C0 norm, the norm in corresponding to continuous metric, then you have actually stability. Okay, so at least as far as the very weak norm is concerned, there's stability. Okay, so another way to think about this more globally is to say that, well, suppose the Kerr exterior region is stable, and you might have recall many of the earlier talks in this conference that concerns that problem. So let's say we expect that to be true, then in fact small perturbation of Kerr of course leads to Cauchy development such that the exterior region is stable, but because the region is stable, the theorem tells you that you will still have a null Cauchy horizon. Okay, so the theorem again in picture. So this is to say if you have solutions in the exterior, let's say converging to some Kerr. Okay, so the paper that we have released said that if you have convergence actually on a space-like hypersurface, but can be very close to the event horizon. Suppose you have convergence here, then in fact you have Cauchy horizon. Okay, and a global version of this theorem is to say that if you have globally data which is close to Kerr, then in the exterior you converge to Kerr, and then okay, in the interior the picture looks exactly like this, and in terms of C0 norm, everything is close to Kerr. Okay, But this is not the end of the strong cosmic censorship conjecture. Well, because even though in C0 norm everything is good up to here, it is still consistent with the possibility that higher norms blow up. Okay, and this is indeed what one would still conjecture. Well, for instance, looking at our proof, you will see that we have to fight against things sort of possibly blowing up in higher derivatives. Okay, so one conjecture one would have is that if you look at generic small perturbation, of course, Kerr itself you would have a smooth Cauchy horizon, but if you look at generic small perturbation, then you get a singular Cauchy horizon. So this is still an open problem, but there are progress in strictly symmetric models that one understands this problem. So here's the theorem. Maybe let me split it into two parts. So I want to look at strictly symmetric models. So let me look at Einstein Maxwell scalar field. And in circle symmetry, I look in the setting that I have two-ended asymptotically flat data. Well, so the first result that one has is you can think of as the analog of my result with the Fermus, but now in spherical symmetry, without any smallness assumption, is that you would always have some Cauchy horizon. Okay. Right. If your initial data is such that you have, if your initial data is such as charged, okay, so you always have some Cauchy horizon, like the picture before. On the other hand, you can find an open and dense set of data, such that if you look at the solution, it is not C2 future inextendable. So this is a result I proved with Sung-Jin Oh in 2019, and more recently, SPSK has improved this to show that in fact you can't extend in C1. So indeed, generically, you do have some singularity, at least in this strictly symmetric model. This conjecture is true. But one important thing in the proof of this conjecture is that in order to prove this part, second part of the theorem related to this conjecture, is that one shows that, generically, that's to say for solutions arising from the open and dense set of data, the scalar field actually obeys a lower bound in the exterior. Okay, and this is the kind of tells that I want to think about that relates to the interior structure. So more precisely, in the result that I obtained with Sung-Jin in 2019, it roughly goes as follows. Okay, so you do three things. So again, you look at this strictly symmetric model, Einstein Maxwell scalar field. So you consider this number. Okay, this is just a number, right? It concerns some limit of some quantity of your spacetimes at null infinity. Okay, so this is your Penrose diagram. Okay, and I just want to integrate something along here. Okay, so this is this integral u from minus infinity to infinity. Yeah. So look at this number. Every solution, you can compute this number. Okay, if phi is identically 0, if the 0 solution, then this number is 0. But however, I say that as long as this number is non-zero, then I attain a tail along the event horizon. Okay, in an average sense, not pointwise, but there's a tail along the event horizon. So that part one of the theorem. So this is to say that you understand something at infinity, you know that there's a tail. Okay. Part two of the theorem tells you that if you have a tail, that's to say if the conclusion of part one holds, then in fact you are singular. Your maximal Cauchy development is C2 future inextendable. Okay. Part three of the theorem says that look at generic data. There's open dense set of data such that this number is not 0. Okay. Putting these all together, you know that there's generic data, so that L is not 0, so that you have a tail, so that the interior is singular. Okay. So this already tells you that in order to understand interior singularity, to understand the conjecture that we're interested in, it's important to try to understand tails. Yeah, so that's what I want to think about. So of course we have heard about this morning, right? This morning we have heard about tails from the nice talk of CMR. And you can already think about this, as we saw in that talk, as a linear question, asking, suppose you look at fixed curve. Now you can look at the fixed wave equation. For instance, you look at the wave equation, scalar wave equation, or the Tarkovsky equation. Okay. Now you want to understand the same questions as before, right? First of all, do you have a tail along event horizon? Can you characterize it with some conditions from infinity, for instance? Now, if you have a tail, can you say that the Cauchy horizon is in fact singular? Okay, well, the solution is singular at the Cauchy horizon. And turns out all this now can be done. So here's the theorem. So let me state it in two parts, right? So Tarkovsky, let's think of the S. You have a Tarkovsky, you have a parameter S. S equals 0 is the scalar wave equation, the perhaps simplest model that you can think about this question. S equals 2 is the Tokosky equation coming from gravitational perturbation, perhaps most relevant to the actual conjecture about the perturbation in vacuum. Okay. So in the S equals 0 case, this is first done with two very different proofs, actually, by Hinz and Aristarchus and Galopoulos-Gaish. And as we heard this morning, now in the S equals 2 case, Ma and Zhang were able to adapt and extend the proof of the second group, Aristarchus and Galopoulos-Gaish, to actually also do the S equal 2 case. And the statement is the following. The statement is that in Kerr, okay, there's subtlety in Schwarzschild, but okay, let's just look at Kerr. If you look at solutions with generic compactly supported data, then you have some tail. Okay, and this tail is even pointwise. You have some pointwise tail along the event horizon, in particular, upper bound, lower bound. Okay. So now this first part. Now the second part of the theorem tells you that okay, this is exactly what you have, and this is exactly what you need in order to show that things are singular. And again, you can split into S equals 0 and S equals 2. S equals 0 is understood first in some old work I did with Spearsky. And very recently, Spearsky also extended this to S equals 2, actually with a completely different proof. Okay, the original proof doesn't seem to work in the S equals 2 case. So the statement is, suppose you have a tail, as in part 1. In fact, you only need an L2 average tail, but let's not worry about that. Suppose you have a tail along the event horizon, then the solution is indeed singular in the Cauchy horizon. Okay, so this seems like very useful progress. Now you understand exactly the tails for a linear equation on fixed curve. And now, once you understand the tail in the exterior, you also know that the interior is singular. Now it looks like that now we should try to move on to the nonlinear problem and try to see if we can actually solve the conjecture to show that indeed strong cosmic censorship holds in the sense that for generic data, the Cauchy horizon is singular. Okay. But before we actually think about nonlinear problem, and okay, I won't be talking about the nonlinear problem in this talk. I want to say that there are in fact two tails. Okay, as we're trying to understand this, we realize that that there's another mechanism coming in which is not entirely linear. It's somewhat nonlinear if you think about the full problem, which is the following. Okay, so what I'm going to try to talk about in this talk is I want to say that, well, okay, in the linear case, one understands these tails completely, and okay, these tails indeed determine the singular behavior in the Cauchy horizon. But if I'm not in the case where I have exact stationarity, that I have, let's say, exact curve, if I have something that approaches curve, which is what would happen if I'm in a nonlinear situation, even the approach is extremely fast. Okay, even I have something dynamical, but it approaches curve extremely fast, the tail has to be modified. Okay, so that is to say, one expects that this is not the answer. The rate of the tail is different if you're in a dynamical situation, and hence the title that we have two tails. Okay. In order to explain that, let's go back to sort of the very beginning of tails, which is the story of Price. Right? So here's a paper of Price from 50 years ago now. And it's in this paper that Price observed that, okay, if you look at Schwarzschild, look at this wave equation, the solution should attain a tail at late time. Okay? And here's roughly what he says. So suppose you look at solution to wave equation. Suppose it's initially compactly supported. Suppose it's on a fixed spherical harmonic. Okay, so that is to say, because I use that Schwarzschild is strictly symmetric, I can decompose into modes, and okay, you can solve in every mode. And okay, if you have each mode you solve, and then there should be a decay rate given by this. Okay, so if L is 0, you get -3. So this is the slowest decay mode, is the L equals 0 mode, 2 to -3. And the higher every higher mode, you gain 2. Okay, so L equals 1, it's -5, and so on. Okay, so that's the expectation of Price. And this now is a theorem, at least in the way that I've stated it, about wave equation on Schwarzschild, which is compactly supported. Okay, so let me try to explain this theorem. There are a few, so that there are different progress, there are different kinds of things you can ask. And in particular, you can first ask about upper bounds, and then you can ask about lower bounds. And you can first ask about the full solution, and you can ask about whether you do have the improvement that's expected from price when the angular momentum. You're thinking about high spherical harmonics. Okay. So this is at least how I want to organize the known results. So the first result I want to think about is an upper bound result. Okay, so this is associated with these various names. So the work of Dafremis-Rodniansky and the work of Tonninger Schlag Sofer solves this maybe up in the case of, in this case, the little bit of loss in spherical symmetry. Okay, but then Tataru and then Metcalfe, Tataru, Toinanu prove this in general without the spherical symmetry assumption of the wave, and in fact with these two proof are very different. Okay, so what's the statement? The statement is that, well, you have actually an upper bound for the full solution. Okay, so you actually can show that the full solution decays like -3. Okay, so in particular, consistent with this expectation, because okay, every higher mode decays faster. So now, if you want to get the improvement or in L, right, the first result was achieved by Tonninger, Schlag, and Sofer. What they showed is that if you are supporting the L spherical harmonic mode, you actually get improved decay for every increase of L. Notice that this is not exactly what here. This is 3. This is 2. Okay, slightly slower, but nonetheless, this is an upper bound. And as long as L is bigger than or equal to 1, this is better than this bound. Okay. Now, much more recently, Angelopoulos, Aristarchus, Gaish, and Hinz independently, and actually with very different proof, shows that in fact you actually have, first of all, an improvement that's -3, -2L as predicted by Price. And secondly, they also show that you have both upper and lower bound. In fact, they actually show that this is equal to this plus something that decays faster. Okay, so you have an exact tell. Okay. So let me further remark on this result. So, well, a lot of these results are actually more general than what I've stated. There's to say it's not just Schwarzschild that's known. And in fact, the approach of Tataru or Metcalfe, Tataru, Toinanu, they actually allow for a general class of space-time under sort of general, for instance, asymptotically flat, a certain stationary estimate assumptions. They have they can prove the T⁻³ decay. And interestingly, actually in the work of Metcalfe, Tataru, Toinanu, they can also think about dynamical space-times. Okay, so the approach allows not only for stationary space-times like Kerr-Schwarzschild, but for instance, things that approaches Kerr-Schwarzschild. Okay. Now, precise asymptotics, as you say, upper and lower bounds, right? This kind of thing. It's also known on more general spacetimes, for instance, in Rice-Nordstrom and Kerr. But all of these precise asymptotics results, they are known in the case where the spacetime is stationary, unlike the upper bound result where you have results on dynamical spacetime. And I'll explain something later and talk about why this is the case. So one has very precise results. For instance, so these are in the works of Hinz and Angelopoulos, Aristarchus, Gaish. For instance, Angelopoulos, Aristarchus, Gaish have very beautiful results on Kerr, because Kerr is not strictly symmetric. You have to think a bit before think about how to think about modes. And turns out there's some subtle behavior about long time dynamics. So this is all understood in that work. Okay, but in both of this approach, somehow one relies on stationarity quite seriously in different ways. Somehow Hinz has an approach which is for analytics, so you have to take Fourier transform in T. Okay, so that requires stationarity. Here, it comes in a very different way. They have to invert the time derivative. Okay, and in that process they use the stationarity. Okay. So that's and then there are many more results, and you can have much more precise information, as I just said. You can have extreme case, and there are really many people who have worked on this problem who unfortunately I won't be able to explain all of them. So there's first sort of works from the physics, sort of before these dots, including sort of many numerical work, and then there are lots of work for mathematics. Okay. Okay. So now I want to understand where these tells come from, and I want to understand what should I expect, and I want to prove a theorem. Okay. So let me first think about the simplest possible case of that I can think about for tells, which is Minkowski. Okay, and you say I'm crazy, and you would be quite right, because there's no tell on Minkowski. As we know, there's strong Huygens principle. If you look at initial data which is compactly supported, let's say here. Now, of course, finite speed of propagation tells you the solution is in the cone here, but strong Huygens principle tells me that everything is really supported here. Right? So in particular, this is 0, and okay, you decay very fast on any compact set. Right? It becomes 0 eventually. So now, okay, so what is there to understand for Minkowski? Well, it turns out for Minkowski, there is still something to understand, which is you want to understand tells when the initial data is not completely supported. Okay, in that case, then you do have tells, but that's coming from trying to understand, okay, data have some tell, and you want to understand how that tells propagate. Okay. So again, in Minkowski, you can only understand this when your data already have some tell. So let's look at my data. So this is Minkowski. Let's even look at the cone. Right? So let's look at the cone. So suppose I look at the data. So this is cone, initial cone, and I want to understand phi initially on the cone. Okay, suppose it has a tail there. Now I want to understand now, if I try to look on a fixed curve moving t, what's the decay rate, right? That's what I want to do. And this is Minkowski, right? So in principle, everything is explicit. You can compute turns out, at least for me, the computation is not so direct, but look at everything is explicit computation. Okay, so what can you do? So let's first, for instance, look at phi, and suppose look at the circularly symmetric mode. Okay, so I call this the L equals 0 mode. Okay, now I want to say the initial data, right, is on this cone. Okay, so now this is as this goes to infinity, the radius of this cone goes to infinity. So let's parameterize this by R. Okay, so suppose here there's a tail. Okay, so let's say this, suppose this is R to the minus K. Okay, so now you can compute, right? You can ask, okay, now suppose this is R to the minus K. Okay, now what is the decay rate here? Okay, so now you compute and you say that, well, phi, right? So suppose I on a compact set, let's say x less than or equal to R. Okay, and you can see that, well, in fact, you would exactly have this much decay. So the decay would be t to the minus k. Okay, but you have to be a bit careful. This is not always true. This is true if k is an integer, and if k is bigger than or equal to 2. Okay, what happens if k equals 1? Right? You can ask this. So you can ask, what about this? Right? It turns out this, you have no tail. You have something that looks like the strong Huygens principle. If you start with this, now you compute, okay, it becomes 0 eventually. Okay, so already there's on Minkowski, there's something interesting to understand, and it turns out that as I will try to argue, most of what's going to happen is just you're trying to understand these. Okay, now let's think a little bit more. What about L equals 1? Okay. So you look at the L equals 1 mode, and suppose this is again R to the minus K. And it turns out that what's going to happen is that you're going to decay faster. T to the minus K minus 1. Okay, if your L equals 1, you gain the power, but you lose right? So you lose the power of R. Okay, so that's to say of absolute value of x. So in a compact region, you decay faster, but still there's something amusing here, which is if you look at k equals if you look at L equals 1, you actually need the k to be bigger than or equal to 3 in order to have a tail. Okay, and if you look at L equals 1, and if this is R to the minus 1 or R to the minus 2, then you have no tails. Okay? And the story continues, right? So the story continues, right? If you look at general L, then this is, as you can maybe guess, so this is t to the minus k minus L or to the L, but this only happens if k is bigger than 2 plus L, right? Otherwise, no tell. Okay. So this is sort of very simple. This is just Minkowski, right? Okay. So why is this relevant to anything? This is direct computation. So now I want to understand why is Price law true. Yeah. Xian.
Hey, Jonathan. So
Yeah.
I want to ask the case of k non-integer case.
That's a good question. Yeah. So let me
And by the
know.
way, so here it's exactly like R inverse, no like O of R to the minus 2, for instance.
This is exactly.
Like
So
exactly like
this is exactly
up to some constant. Okay.
Up to some constant. This is equal.
Oh, okay.
This is equal, and this has some constant. Yeah.
Yeah. Okay.
Yeah. So you can try to understand the case where, for instance, k is bigger than 2 but not an integer, right? 2.5. In that case, it's not so difficult to get an estimate of that, but the exact computation becomes harder. Okay, so here I'm just doing things which you can compute. Yeah, and this would be the most relevant things for what's to come. Thanks. So okay, so now I want to understand the Price's law, really the original Price's law, short term, as follows. So what I want to do is the following. I know that the solution, right, in 3D, of course, phi decays like R near null infinity. This I know. And I also know that near null infinity, I can write an expansion. It's locally in the retarded time. I know I can do that. But let's try to sort of follow this through. Now let's try to write this sort of for all u. Okay, so my coordinate is such that u equals constant is these hypersurfaces, right? And R is the usual R, okay? And I use the RU for these x coordinate. And I do an expansion. I expand R phi as phi naught is a function only of u and the angular variables independent of R, and then R inverse, and then a function of u and the angular variables, and so on. Expand until I don't need to expand anymore. Okay, analyze it, whatever it means. I want to think about this. Now, I want to understand which ones of these things have a non-trivial limit as u goes to infinity. Okay, and I claim that you can use the wave equation, can deduce some recurrence. From the wave equation, you can deduce some recurrence relations of these things. From that, you can already do some analysis, and you can try to find which ones, right, the first ones, so that the limit is non-trivial. Okay, so it gives somehow a non-trivial limit. So you think of having something that starts with, let's say, some constant times r to the minus something. Okay, so just find that, and then go back to your Minkowski computation here. Right, if you know it's exactly r to the minus something, you can compute what's the tail contribution. So now look at that, right? Look at the Minkowski thing. Okay, compute the Minkowski tail contribution, and I want to say that this actually gives the contribution in the full spacetime. Okay, it would be exactly this. Well, of course, okay, one has to be a bit careful because, okay, if you're not in the asymptotically flat region, if you're deep inside, one has to be a bit careful. But at least when R is large, this is the exact, I want to argue that this, well, will be the exact tail that you get. Okay, so there's something that happens because of the asymptotic geometry that tells you something about the expansion. And once you understand the expansion, now the rate is really determined by, okay, how the expansion would get the final rate is a Minkowski computation. Okay, so let's imagine this is true. And if this is true, we can already try to understand, well, why Price's law is true. So this is Price's law. Sorry, this is the wave equation on Schwarzschild on a fixed L mode. Okay, so this is the equation. I have to maybe give a warning. So in the last minute writing the talk, I decided to change my normalization of the constant, so I could be off by factors of 2 at several places. But the principle it's fine here. Okay, so I write it down. So assume I have an expansion. Okay, now compute. Okay, so if I have an expansion, I use the wave equation. Okay, so and then I want to get some recurrence relation. I want to say, okay, certain of these would relate to each other and so on. Okay, so first of all, look at L equals 0. So remember in L equals 0, right? I need k to be bigger than or equal to 2 in order to have contribution, right? So this is this statement. K has to be bigger than or equal to 2 to have a contribution. So in other words, this guy doesn't contribute because this is phi is like the order minus 1. So this doesn't contribute. So I want to understand whether these contribute. Okay. So look at the wave equation. Wave equation tells me that this is equal to 0. Okay. So if I'm initially compactly supported, so phi 1 is initially 0, then it's always 0. So therefore, there's not, this term doesn't exist. Okay. So now I look at the next term, right? Now the next term also satisfies a recurrence relation, and the recurrence relation is something looks like this. Okay, so write it down. So M is the short-term mass. Now, if one expects that, okay, if you think about the a radiation field, let's say from Minkowski, you can show that the integral of the radiation field should be non-zero. Okay, so once you can, if you can justify this, then this integral is non-zero. Then phi 2 has a non-trivial limit, and then okay, and then right, this is the main term that contributes, right? So this is r to the minus 2, and another r is r to the minus 3, and if you go back to here, r to the minus k gives t to the minus k, and that's the t to the minus 3 tail. Okay. So you can do this for all different L's. Let's look at L equals 1. So in L equals 1, there are more things that don't contribute, right? Phi 0, phi 1 don't contribute because L equals 1, you move up 1. Okay. So if they don't contribute, let's think of them as will eventually go to 0. Okay. So now let's go to the wave equation. The wave equation gives these things. Okay. So I don't have to analyze phi 1 because it doesn't contribute. So let's try to understand phi 2. Okay. So I want to understand phi 2 whether it contributes. Okay. So I have to integrate this. Okay. So now I'm on Schwarzschild, right? I'm on Schwarzschild, therefore M is a constant. Therefore, if I integrate phi naught, right? What is integral phi naught? Well, integral phi naught is integral phi naught here, which is integral of this, which by the fundamental theorem is phi 1 in the future minus phi 1 in the past, but phi 1 in the future also goes to 0. Okay, so if I integrate this, I know that the integral actually will go to 0. So actually, I know that phi 2 goes to 0. Right? Another way to say this is to combine these two equations, I get this. So therefore, I know this is a constant, so it's always 0. But phi 1 goes to 0, so phi 2 goes to 0. So this also doesn't give rise to the final tail, right? So this is the first gain. This is the first gain compared to the L equals 0 case. Now the second gain is that now you know that the first contribution is this. Now because it's L equals 1, right? L equals 1. If you go back to this table, if you L equals 1, you gain 1 power. Okay, so that's the second gain. Therefore, you gain 2. So therefore, instead of t to the minus 3, you have t to the minus 5. Okay, and this is exactly the prediction of price. Okay. So far so good. This is all just rethinking price, and the claim is that you can make this thinking rigorous and give a proof of Price's law yet another, I mean, this is already known, and yet another proof of Price's law based off this sort of thinking. But now this, you don't have to stop there, because now you can think about things which are dynamical. You don't have to, if you think in this way, you don't have to restrict yourself to stationary space-time. So let's think about dynamical space-time. Okay, so let's think of a very concrete and simple setting for which you can think about dynamical space-times. Let me stay in the world of spherical symmetry. Okay, so this is my world, spherical symmetric space-time. So Schwarzschild is a particular case. Okay, so in spherical symmetry, I can think about the Hawking mass, and I can think about the Bondi mass, which is just if you look at the Hawking mass, right? So M, right? If you take the limit, the limit is equal to capital M, and now this is just a function of U, right? So on every outgoing null curve, I can take the limit. So now I have a function along future null infinity. Okay. In the Schwarzschild case, this is the constant, right? It is whatever you think of as the mass of Schwarzschild. I want to think about the case where it does not necessarily have to be a constant, right? So I'm just thinking of dynamical spacetimes. Here it doesn't. Okay, at this generality, they don't even have to satisfy the Einstein's equation. Okay. So now I want to go back and think right? So what in the previous case, what do I need to see in order to get a tail? So if I look at, let's say, strictly symmetric solution, right? So I go back to my strictly symmetric consideration, which is this, right? So the point is I have to say that what if this is non-zero, right? Then I have a tail. What is this, right? This is, I try to integrate that, right? If I integrate this, it integrates to non-zero, then I have a tail. Okay. So I want to say this is still true in this case for very general strictly symmetric spacetimes, even dynamical ones. So I want to again think about quantity L, which is defined along null infinity. I just look at the analog of exactly this thing, right? I want to integrate this. This corresponds to the first term in the expansion. This is phi naught, right? This is so that I make sure I normalize my u correctly. This is just the mass. Okay, so I look at integral, and I want to say that, well, even if things are dynamical, even if it's not exactly Schwarzschild, if this is non-zero, then I get a tail, which is t to the minus 3. Okay, the same as before. Okay. So actually, there's already some precursor of sort of this kind of thinking so that we still think like this, which is this turns out to be useful in spherical symmetry in the work that Sung-Jin and I did for Einstein Maxwell scalar field, or in some cases Einstein scalar field. And indeed, you can really say that if L is not zero, then you have a tail. Okay, so this is sort of work going back a few years. At that point, we were not able to actually get tails yet. And okay, you can see some of the results were funny because we don't really know what we should be proving yet. But anyways, what we have seen is that if L is not zero, then you can say something that has something to do with tails. Okay, so what we said is that for let's say look at things which are perturbation of Minkowski, for instance. Okay, so in particular, there's no black hole there. So there's nothing, this has nothing to do with black hole. It's just something about the asymptotic flat region. So in this case, what we can say is F is not zero, then we have some upper and lower bound, which is sharp. Okay. Notice that this is really a nonlinear result because everything is converging to Minkowski. In Minkowski, there are no tails. But suppose I have something nonlinear, I have a nonlinear solution. So therefore, there's some math which is doing something. And as long as this quantity is not zero, I have a tail which is determined by the nonlinear part. Okay. Now you can also think about black holes, and the story is similar. You can look at the same quantity L, and if it's non-zero, then you have a lower bound. At that point, we were not able to prove a pointwise lower bound, but nonetheless, we can prove an average lower bound.
Jonathan,
yes.
Excuse me. So this is for a general wave equation. I mean, what kind of equation?
Sorry, here is sorry. So here, these two theorems are Einstein Maxwell scalar field system and spherical symmetry. So they are coupled.
Okay, so so the equation, I mean, the solutions have spherical symmetry, or you are...
The solution has spherical symmetry. So at this point, this is spherical. This is still spherically symmetric. Yeah.
Yeah. Okay.
Yeah. Thanks. Yeah. Sorry, I was not so clear. So yeah. Okay. So let's again. Okay. So maybe say that. So I look at strictly symmetric and dynamical spacetime. I want to understand everything about wave propagation. The first thing I want to understand is, let's say, strictly symmetric wave. Okay. Now there's this setup which is nonlinear but still strictly symmetric, which we understood before, which is in this case, if L is non-zero, then you have a tail. Okay. Then of course, naturally, as your question may be suggesting, then I should next be looking at, let's say, the background is strictly symmetric, but let's try to look at wave, which is not strictly symmetric. What can I say? And here's the theorem, and here's the new theorem. The paper's still in the works. And look at the following setup. So again, I look at a strictly symmetric space-time, right? It settles to Schwarzschild. In fact, in this theorem, you don't even need spherical symmetry, but okay, doesn't matter. So something that settles down to Schwarzschild suitably fast. Okay, so assume something that for instance Sergio and Jeremy can give you. Okay, so it goes. Okay, so so now I want to look at the wave equation, solution to wave equation, and now the solution to wave equation does not require spherical symmetry. Okay, I want to understand that, and the claim is that if L is not zero, so again, this is something you compute at infinity, then there's a tail. Okay. And in fact, generically, you can show that L is not zero. You can show that generically L is not zero, therefore generic solutions have a tail. Okay. So these are, you can get the precise tails on, let's call these ultimately Schwarzschild spacetimes. Okay. But now here's the second tail. I can try to now consider the following problem, which is I look at still now strictly symmetric things, let's say converging to Schwarzschild. Now I want to understand the L equals 1 mode, right? Because this is still strictly symmetric. I can still decompose into strict harmonics. Now the L equals 1 mode is supposed to decay faster. Right? I know the full solution decays like T to the minus 3. The L equals 1 mode, one might think decays faster. And indeed, in the case where you are non-dynamical, you're stationary, it decays like T to the minus 5. Okay. But I want to revisit this. I want to think about this in the dynamical case. Okay, so what's the statement? So I have strictly symmetric dynamical spacetime, right? Strictly symmetric as I have before, converging to Schwarzschild. Okay. Now I revisit the recurrence relation, right? So remember, because it's L equals 1, phi naught and phi 1 don't contribute. So I want to understand phi 2. Okay, I want to understand whether phi 2 has a non-trivial limit. In the case where I am stationary, phi 2 would also go to 0, right? I can combine the two recurrence relation to deduce that phi 2 in fact also goes to 0 and therefore it doesn't contribute. Okay. But now, if you look at these recurrence relation, so what do I have to do now? Well, again, what I have to do now is I integrate this equation, right, to get phi 2, and I integrate this. Okay. It used to be I said that I integrate m phi naught is the same as m times the integral of phi naught because m is a constant, but now no longer m is a constant. I can pull it out to use the first relation, right? And in fact, you can see that if m is non-constant, you can't pull it out. You can cook up phi naught so that this is non-zero. Okay. So as a result, already phi 2 has a non-trivial limit as u goes to infinity. So already this contributes to the tail. And indeed, we can prove this. So this is a theorem. So suppose you have strictly symmetric spacetime, as I just said, converging to Schwarzschild suitably fast. But now I just require that the Bondi mass is non-constant. Okay, so it can converge to a constant sort of crazy fast. I don't care. It can even eventually becomes constant. I just don't want it to be globally constant. Okay, so this is sort of the dynamical assumption. Then if you look at generic compactly supported data, supported on the mode L equals 1, L bigger than equals 1, you can sum over all modes, that's not a problem. But it has to be supported, right, so it has no L equals 0 contribution because that would decay. That would decay like T to the minus 3. Then the tail is T to the minus 4. Okay, so contrast this with T to the minus 5 twice the slow tail. So if you have a dynamical setting, in fact, there's a modification to the tail, and one can prove that this is actually T to the minus 4. Okay. So let me actually tell you the theorem. What is the actual theorem that we prove? So the theorem, okay, doesn't really require on ultimately Schwarzschildianness. In fact, we want to make it sort of as modularized as possible. I want to sort of find exactly what assumptions I need. And essentially the main point I need is I need asymptotic flatness. And I need some sort of elliptic estimates that I will be able to do related to the absence of zero energy and resonance. Okay. So and this is very general. You can do it for doesn't have to be strictly symmetric. So if it's strictly symmetric, you can think about higher L's. Otherwise, you can think about things which are not strictly symmetric, higher dimensions, and so on. But one and you would have a similar. Oh, sorry. You would have a similar phenomenon. There's to say in a dynamical setting, you will see a different tail as in the stationary setting. Okay, and in fact, I claim that this is already seen numerically in some of the numerical works, including some which also try to give some explanation of why this happens. Okay, so here's a theorem, again joined with the Sung-Jin Oh. Again, the paper is in preparation. So the only thing really I want to think about is I want to think about some sort of wave equations. In fact, one can think about nonlinear wave equations, quasi-linear, doesn't matter. Okay, so I have wave equations. Things being in odd dimension is extremely important. Right? Otherwise, of course, even dimensional waves, tails looks very different. Okay, so what do I need? I need asymptotic flatness. So this is like a wave operator. Asymptotically, this part looks like box, and this part looks like they're going away in suitable decay rate. Okay. If d is equal to 3, I need the null condition. Sorry, when I say d is odd, of course, I mean d is bigger than 3. Okay, 1 for me is not an odd number. Okay, so if d is equal to 3, I need the null condition to have the nonlinear. Otherwise, I just need regularity of the nonlinearity. So I need an elliptic estimate that I just said. So this is sort of in the form of the stationary estimate. That's to say I look at p naught, which is to say I look at p, but drop all the possible dt's here. Whenever you see a dt, drop that term. Okay, so then you have an operator. I want that to be an invertible operator with suitable estimate, and I want the following. So I'm actually trying to prove a conditional result. Okay, so that is to say, I already assume phi has some bounds. Okay, so I want to say, for instance, phi is bounded, and if you look at all derivative of phi with respect to let's say Kleinemann vector fields, so it's vector fields that cease null infinity, also are bounded. Okay, so assume, let's say, all of these are bounded for the linear case. Assume it decays a little bit in the nonlinear case. Then I can say that, well, in fact, it decays with a certain sharp rate. Okay, so assume sort of structural conditions of the problem. So asymptotic flatness, the invertibility of p naught, and null condition for the nonlinearity, and assume already I have some weak bounds. Then I can boost it up to strong and sharp bounds. Okay, so the result is that then the late time tails, they are dictated. So how can you compute them? You can compute it by, okay, in general dimensions. Okay, you have to take into account the decay towards null infinity with a different R, but then you do this expansion. Okay, so again, it's exactly as we described above. Look at the first thing that has a non-trivial limit in the future, which actually contributes in Minkowski. So that would give you the tail in the faraway region, and you have a spatial profile if you go inside, and that's determined by the elliptic operator p naught. Okay. So this is the general.
What is the metric? What are the conditions on the metric now?
Sorry. So if you think, yeah. So I just think in terms of just a wave equation like this, if you think it's a metric, then what this says is that it's asymptotically flat. So the metric is asymptotically flat, and then I want the certain. You should think this is certain something like a Morawetz assumption.
So wait, dt means a low order term. That's what you mean?
Sorry. So okay. Sorry. So if I have the sorry. So if I have the basic model is p naught is this, right? This is the wave equation. So p is this, right? So let's even forget all the low order term. P naught in this case is Laplacian. That's to say I just drop all the possible dt you see. Okay. So this is sort of like the spatial part.
Okay.
So if I look at the spatial part, I can invert. That's what I want to say. Yeah. So this is to ensure I can do elliptic estimates in the inside. I mean, because with the potential, things can, right, in the finite region can be very complicated. I don't want to think about that. I just assume that I have something like that.
And there's nothing about the positivity of the potential or anything.
Well, everything is smooth. Yeah, but otherwise, everything is smooth and decays at R goes to infinity.
Yeah.
Okay. Yeah. Okay, so now let's come back to the strong cosmic censorship problem. So we know somehow from the theorem and the analysis of the recurrence relation that one expects that if you have a dynamical spacetime, you expect a correction to the tail. So in fact, it seems reasonable to conjecture that, right, so these higher D and higher L's problems, of course they are, okay, you can think about them, but really I want to think of them as models for higher spin. Okay? So if you think about those as models like that, then you may expect that if you look at the Maxwell spin 1 perturbation or gravitational perturbation spin 2 perturbation, but now of course in dynamical setting, you have a correction to the tail. And that is to say, if you look at Maxwell on something settling to Kerr, let's say you expect T⁻⁴. If you look at perturbing Kerr, like with the Einstein's equation, you expect something T⁻⁶, in contrast to T⁻⁵ and t to the minus 7 in prices prediction. Okay, so this is a dynamical thing. And maybe this is a good point to remark the following. Actually, there is a Maxwell result on upper bounds by Metcalfe, Tatarito, and Anu. Maybe it was even also mentioned in CN's talk in the morning, which only proved t to the minus 4, right? So one may think, okay, they didn't get the sharp thing. But okay, indeed, if you believe in this conjecture, right, because their assumption allows for things which are dynamical. So then actually, if you believe in this conjecture, the upper bound is already sharp. It's not that the method doesn't get the sharp thing, it's that the assumption probably does not allow that. Okay, so let me finish at least this part with another example. Since I told you that one can think about nonlinear things. So let's try to think about nonlinear thing. I want to think about wave maps. Okay, right, so one can think the following. So you have some stationary thing, that gives you some tail. Okay, if you perturb with a non-stationary dynamical thing, that can give you a correction to the tail. In fact, you can also perturb with a nonlinear thing, which gives you a correction to the tail. Okay, so let me just look at the simplest nonlinear problem already on Minkowski. Okay, so I want to look at wave maps. So what's this? So this is I'd start with R3 plus 1. And I want to map to some manifold. I don't know. It doesn't matter. Okay, it can have topology and so on. Sorry, sigma. Okay. So and you think of what's the look at the suitable Lagrangian, and okay, the natural thing you come up with would be the wave map equation, and in local coordinates it's this gammas are the Christoffel symbols. Okay. So now what we want to say is the following. Look at a particular map where you map everything to a point, which is this point P, let's say. Maybe that's a bad color, P, okay? So that's a certainly solution, and you can perturb that, okay? A very classical result, proved independently by Christopher and Kahneman already in the 80s, is to say that, okay, the constant maps are stable. Okay, if you perturb, then in fact, you look at the solution, they are global, and they converge to constant. You may want to ask, what can I think about the tails here? What's the convergence rate? Okay, and turns out the convergence rate depends on gamma. And more precisely, it depends on the curvature at the point P. So here's what one can deduce as a consequence of the theorem I showed you before and some analysis of the recurrence relation. Oops. This, sorry, 3. Sorry. Suppose the Gauss curvature at the constant point that you want to think about, it's non-zero. Then you look at generic initial small data. The solution decays like t to the minus 3. Okay. If at that point the Gauss curvature is 0, then it decays faster. You have an upper bound of t to the minus 4. Okay. If the Gauss curvature really vanishes like crazy, let's say it vanishes in the neighborhood of P, right? Then there's no tail. It decays faster than any inverse polynomial. Okay. One can.
Wait, so this is a statement about a point and a neighborhood of the point in the initial data. That's what you are saying?
No, sorry. So okay. So the point is this point.
Yeah.
The map I want to consider is okay. So there's the map that I can have, which is I map everything to P. That's a constant map.
Okay.
And I want to perturb this, right? I want to think about perturbations of a constant map to P.
Sorry, I apologize.
And okay, and the long time dynamics, it's determined by the curvature at the point P.
Mm-hmm.
So of course, okay, one can imagine a result which says that okay, you can try to understand the order of vanishing and get different decay rates, but okay, but the computation got too messy, so that's all we did. Okay. So I suppose I have 2 minutes. Maybe I can still say something about the proof. The proof is really trying to make rigorous the ideas I try to outline, which is to try to analyze the recurrence relation at infinity, and then try to say everything else should be like Minkowski. Okay. So it's an iteration argument. Okay, so because I already start with some estimate that I assume, right? So I actually don't think about anything like boundedness. I don't think about that because I already have L infinity estimates, I assume. Okay, so I just iterate. Okay, I want to every step I improve something until I cannot improve. So I divide my space-time into regions, right? So let's think of the black hole case, right? So it's a very far away region, intermediate region, and a near region. And I want to iterate sort of, and analyzing the expansion infinity allows me to improve a little bit inside, improving a little bit inside allows me to analyze the expansion infinity better, and I just continue this iteration. Okay, and I in this process I allow loss of derivatives as many as I can. I don't care. I allow loss of vector field bounds. Okay, so these are things I can deal with. Okay, so okay, so there's sort of two parts, right? One part is the outside. The outside is I want to justify this expansion, and then I use the recurrence relation, right, that we have seen some manifestation of those in some earlier slides. And this part we really rely on a lot of these technology that introduced by Angelopoulos or Takis-Gaish, but we only need it sort of at infinity, right? So we don't need any sort of global application of RP and so on. It's only at infinity, and sort of in very, very rough terms, sort of one thing is I want to commute with this conformally regular commutator, because this thing allows me to pick up different things, right? Because for instance, this hit on here would kill it, right? And then okay, and it hits on this twice would kill it, kill this one, and so on. Right? So this allows me to sort of tell me which term in expansion I'm controlling, and then I have to try to really prove estimates, and here is where I need to use the Differential-Raniansky RP method to handle the higher envelopes. Okay, so these are okay. So let me one word summaries. I try to use the technology of Angelopoulos or Takis-Gaish. Okay. But now one of the new key is I want to ask, how do I propagate the estimates inside? And I really do what I just told you, which is I try to think that all the propagation to inside is Minkowski. Okay, so there's an intermediate region where I just want to show that, okay, first of all, the terms that don't contribute, right, in Minkowski, they really don't contribute. And second of all, the tail that's given by what I want is the Minkowski contribution. Okay, so I do exactly this. I write the box as Minkowski plus beta. Okay. Now you want to just estimate the beta, and you say that because okay, it's a variety of decay, you can estimate that. And it turns out one of the key is the following. One of the key is that the reason that you can say it's better, right? If you do it naively, it will seem that you lose in the scale, that your estimate don't improve. But actually, because I write everything at Minkowski at the main term, I can actually use strong-Huygens principle to say that, well, in fact, I only have to consider a smaller set than I would otherwise be thinking about in order to control the error term. Okay, so even though okay, strong-Huygens principle, of course, is highly unstable, we know from the result, but in the proof, I actually use strong-Huygens principle to control the error term. And then finally, in the near region, everything is about using the invertibility of P naught to propagate the estimates inside. And this part of the argument, right, as the far away part, we sort of learn from Takis and Angelopoulos-Gaish. The inside part we learn from Metcalfe, Tataruto, and Elo. Okay, so I think my time is really up. Let me skip the final slide. But thank you very much for your attention.
Thank you, Jonathan. All right, so questions. There's a question in the chat.
That's a great question. So can everyone see this, or should I read it? So the question is, can you iterate the method to understand the next to all the next to leading all the time? Actually, we cannot. But it doesn't seem we've thought briefly about. So actually, there's some quite amusing thing here to say. In one of the works of Takis and Angelopoulos-Gaish, they were able to do that. They were able to understand the next term, which has a log in it, and the constants relates to the constant of the first term, and that's very nice. And it seems to us that in their proof, it's important that they were in double null coordinates, for instance. So in the coordinates that we work with, we can't catch that. So it seems that there's something quite subtle to try to catch the next order term in such a general sense. So the short answer is we can't do that. Yeah. But that's certainly interesting.
Maxime?
For the amazing talk, Jonathan. Small question. So you say the potential has to be asymptotically flat presumably it cannot go too fast to 0 because it has to be at least like Schwarzschild. Presumably it also cannot.
So it's it has to be if you want V has to be all to the -2 minus epsilon.
Plus epsilon, you mean, no? Oh yeah, well,
yeah,
faster, yeah, okay, yeah,
depending on
that's
whether
exactly
you
what I
put
thought.
brackets, yeah.
That's really what I thought. Yeah, because if it's exactly equal, then you have different scaling, right? Okay.
Right. Actually, there is something you can actually do. You can actually allow U to the epsilon over R to the 2 plus epsilon. So you can allow something scales like 1 over R squared, but okay, it has to be something like that.
And you would still get T to the -3?
You can get whatever is determined. Oh no, well, you can get whatever is determined by the expansion.
By the tail, so you will lose a little bit. Yeah, okay. Very nice. Thanks.
Yeah, now that's also a great question. So there's another question in the chat. Can I do it in even dimension? So this doesn't, at least as it is, doesn't work in even dimension. So yeah. So one explain in even dimension, what you see from Minkowski is stable. So perhaps that would be the result one wants to get. But no, what we're doing doesn't work.
There's a hand raised by Sergio and then by Sia. So let's start with Sergio.
Yeah, no, I wanted to understand more about what you said, the fact that you can use the strong Huygens principle in Minkowski. That sounds surprising. So what?
So okay. More? Yeah, the way I say it maybe made it more.
Probably you have something more stable than that, right? I mean, in the sense that you have something more quantitative than just the strong Huygens principle.
It's actually mainly that, but the point is that the main thing I'm computing is the Minkowskian box. So when I try to control the error, I'm trying to control really Minkowski box inverse of certain things, and then I want to show that the rest is better. And the statement is simply the following. The statement is
you use a fundamental solution of the Minkowski space. That's what,
no, we use something much weaker. We use something. So let's look at this. So let's look at this is R equals R. It's only outside where things are asymptotically flat, and I can use this kind of idea. So if let's say I want to estimate a point here. Okay, I want to estimate the point here. So if I just use finite speed of propagation, I have to estimate my error term in this region, right? But I want to say that in fact it suffices to estimate all my error terms in this smaller region, and that's important. Yeah, so that's really is the what I'm using. So somehow, so I start with some pointwise estimate, right? And then I have to improve. Okay, so I have to integrate up some pointwise estimate. The point is that because of strong Huygens principle, I can integrate on a smaller set.
So you're actually using you're not using the fundamental anything about you don't need a construction of a fundamental solution or anything like that.
No, we don't need that.
Even a weak version of the fundamental solution. You just use a strong Huygens principle. That's it, from what I understand, right?
Yeah. Well, okay. Well, here, yes, yeah. For this part of yeah. There are certain arguments which I really use Minkowski computation, right? So I don't use the fundamental solution per se, but for instance, I actually use explicit computations on Minkowski. This I use.
Ah, okay.
Yeah. So this I use.
So when you say that you need the assumptions of boundedness, so you assume that you have a solution of whatever nonlinear equation, which is bounded. You don't need anything more, or
sorry, I need a little bit of decay. I don't remember the exact. I don't remember. So okay. So for linear, I really don't need anything more. So for linear, I just need that phi and all the vector field bounds hitting on phi. It's I don't even need bounded. I need phi and all the vector field bounds hitting on phi to grow at most polynomial. That would be enough for linear equation. For nonlinear, I would need a little bit of decay, but that decay that I assume would be less than what you would have. For instance, would be less than certainly less than what you would get from your proof. So let's say I assume whatever decay that you gave me from your proof, then I can already start the process to iterate.
I see. So in particular, this will presumably work also for Kerr for small a.
Yeah, that's the hope. Okay, there's some there are a few things that has to be done there. Yeah, but that's the hope, of course, to do that.
There's a question in the chat, and then there's a raised hand by Sue.
So should I do the chat question first?
Whichever if you can answer the chat question quickly, yeah, sure.
Okay, sure. Yeah, thanks, Leonard, for the question. Yeah, that's a great question, right? So since he asked that question, maybe I should also mention some nice work that Leonard has done, which is one expects that in some dynamical setting, let's say related to formation sort of collapse of stars, you expect that at infinity you don't have expansion in 1 over all, you have some log terms. So our methods actually also work. So at least in fact in the paper we include also, so you can allow for log terms. You can't allow for sort of fractional powers of R. That would be problematic. But if you have something like log R over R, that you can all put that in. Yeah, there's no issue.
Okay, and there's a raised hand by Suya.
Hi, Jonathan. So maybe you can go back to this quasi-linear wave.
Yep.
I mean, the main result.
Yeah.
One of the main results. Yeah. So how general is this latent tails? I mean, so you mean this is like you get like, for instance, L equal to 1 mod T to the -4 generically?
Sorry, for the nonlinear.
Yeah, for this nonlinear. Yeah. So
yeah.
I don't
So
understand the conclusion. Yeah.
Yeah. So it's whatever determined by this, and really one has to do a case-by-case analysis. So there's to say, for instance, if you look at wave maps, right?
Okay.
Even on Minkowski, then okay. Of course, on Minkowski there are no tails, but if you look at the recurrence relations, you can see that if you look at the wave map case, you would get a contribution on some of these, and that would determine the latent tail. And okay, when you do that computation of trying to understand the recurrence relation, that's where for instance, the curvature comes into play.
Okay, it's like you apply this result to some specific models.
Right.
Okay.
So the only thing that we have computed, in fact, is wave maps and
okay.
And whatever it's called, vanishing mean curvature. So the hyperbolic minimal surface equation. So those one can compute, one can know that. But yeah. So that one has to do sort of case by case.
Thanks.
All right, let's thank Jonathan.